In Australia, the killing of humpback whales was banned in 1963. At the end of 2018, 45 years later, well, this is interesting in the spec exam, that's actually 55 years, the population P of migrating humpback whales off the coast of Western Australia was estimated at 30,000. Now, I'm going to work with the true figure of 55. Assuming that the population of humpback whales had been increasing at an instantaneous rate equal to 10% of the population, estimate the number of humpback whales at the end of 1963. So the information they give us here is that dp dt is equal to 0.1 p, so 10% of the population. So we know that that would have a solution. P is equal to P naught E to the 0.1 T. And they're telling us that 30,000 is equal to P naught E to the 0.1 times 55. And we can solve for that on the class pad. So we want to solve 30,000 is equal to, let's just call it x, that's the only unknown, e to the 0.1 times 55. And execute, and that gives us 122.6. So let's call that 123. To model the growth in the population from the end of 2018, a marine biologist suggests that the rate of growth be modeled by the equation below, which we can recognize as a logistic equation. The biologist redefines P0 is 30,000, so T is the number of years from the end of 2018. If P of T is written in the form Pt is A over 1 plus B e to the negative ct, we need to determine the values of the constants A, B and C. And in order to do this, I went to the formula booklet. Now if we just expand this one out, dp dt is going to be rkp, take away rp squared, and to get this in the form that we've got here with a 1 there, what we need to do is divide top and bottom by p naught. So we're going to just have k on the top, and then we'll have 1 plus k minus p naught over p naught e to the negative rkt. Now if we compare our equations, so rp squared and p squared over 700,000, that's telling me that r is 1 over 700,000. Now also comparing here and here, we can see that rk is equal to 0.1. Well, that would tell me that k is equal to 70,000. So we can see the k is here, same as the a, so that's given me that a is equal to 70,000. So that's one of the values. Now b is going to be this, k take away p naught over p naught. Well, our k value is 70,000. P naught we know is 30,000 over 30,000. So that's 40,000 over 30,000. B is going to be 4 over 3. And in here we've got RK, we know is 0.1. So that's the C. So C is 0.1. hence determine the year during which the population of humpback whales off the coast of Western Australia will reach double the estimated at the end of 2018. So if we go back to our equation, we now know that the A is 70,000, and on the bottom here we're going to have 1 plus 4/3 of e to the negative 0.1t. And the estimate at the end of 2018 was 30,000, so we're wanting when p is 60,000. So we've got 60,000 equals 70,000 over 1 plus 4/3 e to the negative 0.1t. And to solve that, we're just going to use the CAS. So, solving that gives us that t is equal to 20.79, so sometime between 20 and 21 years. So it's going to be during the year 2039. So we're asked to state the major difference in the variation in the population using the model in Part B compared with Part A. Well, Part A just gives us exponential growth. So basically just like that. Whereas Part B, being logistic, is going to have the situation where it starts off growing very quickly, but then it will taper to this asymptote.